Let's have a look at an example where dot products are used in proofs. In this particular proof, we're being asked to prove that the diagonals of a rhombus are perpendicular to each other. Now the key connection here with the dot product is the words perpendicular to, because if we examine the dot product formula, we can see here that the dot product is equal to the magnitudes of the two vectors a and b multiplied together, multiplied by the cosine of the angle between them. We know that the angle between them will be 90 degrees if we can show that cosine theta equals 0. There's a direct connection between cosine theta equals 0 and an angle being 90 degrees within a triangle. So that's the connection for the dot product. If we see the words perpendicular to, it suggests that dot product may be a good way to go to actually prove this particular conjecture. So to commence our proof, what we'll do is we'll label two sides with vectors a and b. That's OA and OB respectively. Now if we want to prove that the diagonals are perpendicular, what we need to do is look at establishing the diagonals OC and AB in terms of their vector equations. So OC is equal to OB plus BC, and in terms of our original vectors A and B, OB is B, the vector B, and BC is parallel to the vector A because it is a rhombus. So we can write BC as the vector A. The other diagonal is the diagonal AB, and we can express that in terms of AO plus OB. Now AO is the negative of the vector shown as A, and OB is just the vector B. So there's our two diagonals in terms of our vectors A and B. What we want to do now is use a dot product. So it's OC dot AB, and our aim here is to show that this dot product is equal to 0. So I'll write our vector equations for OC and for AB, and we can expand these brackets like we do in algebra. So maintaining the dot product, it's B dot negative A for the first terms, and then the outer terms of the bracket are B dot B, and then the inside terms are A dot negative A, and then the last terms of the bracket gives us A dot B. We'll simplify some of these before we go any further, so we can write the first dot product as negative B dot A, and then using the formula for dot product, we have the magnitude of vector B multiplied by the magnitude of vector B multiplied by the cosine of the angle between the vectors, which in this case we'll call theta, and then we have minus the magnitude of vector A multiplied by itself multiplied by cos phi, the angle between vector A and itself. And then we've got the addition of A dot B. Now we can cancel out B dot A and A dot B because we've got the negative of one and the positive of the other, and the order for dot product is not relevant, so it's commutative. B dot A is equal to A dot B. For the remaining terms, because we're considering an angle between the vector and itself, the angle will be 0. So we've got the magnitude of B multiplied by itself, which is the magnitude of B squared. And the cosine of the angle between those two vectors is 1 because the angle is 0. And the same applies for the magnitude of vector A squared for the remaining term. Now because this is a rhombus, all sides are equal in length. So the side represented by vector B and represented by vector A are both the same length. So we'll substitute the magnitude of vector B in the place of the magnitude of vector A. And when we do that, the difference between those two new magnitudes is equal to 0. So we've shown that the dot product between the diagonals is 0. And going back to what we said earlier, if the dot product is equal to 0, that means the cosine of the angle between the vectors is 0. And that means that the angle must be 90 degrees, given that we're only dealing with angles between 0 and 180 degrees.